Welcome to the next lecture on laser based process part 2. In the previous lecture, we have been discussing system setup of AM machine. We saw little bit of fundamentals of laser theory, then laser components, continuous laser and pulse laser we saw. Now, we will try to see various lasers. In this various lasers, we will try to see solid state laser, gaseous laser, fiber laser, how does it work. In this chapter, finally, we will see some of the laser beam properties. Generally, at IIT Kanpur, we offer a full course on laser fundamentals. Since laser is part of this additive manufacturing, we are just superficially brushing through fundamentals of laser, which will help you to understand while doing machining or while making prototype or while evaluating prototype or the final product. Different types of laser. Laser are classified by different parameters, but most are categorized by the active medium. The laser is grouped under solid state laser, gaseous laser, liquid dye laser, semiconductor laser and fiber laser. So, the difference if you see, it is in the gain medium. So, you can have a solid state, you can have gaseous, you can have liquid dye, you can have semiconductor and fiber lasers. Each one of them have their own particular requirements in terms of lambda and in terms of peak power. So, what you can get here in the other thing you cannot get. That is why we have so many different types of laser. The laser can produce finally a coherent light at different wavelength and the output beam can be either continuous or pulsating. So, this continuous pulsating will be taken care by Q switching and mode locking facilities which are added to the system. Solid state laser, the gain medium is solid at room temperature. It started way back in 1960, but the maturity level started to come into existence after 1980 in various industries. In 1960, the first solid state Luby laser was invented, but it came into industry into fullest extent after 1980. So, it is typically only 50 years old. The first laser used Cr3 plus impurities. Most solid state laser embedded a dopant in the host material. The host material is Al2O3. In that material you have this. Niobium is another common dopant in commercial laser today. That is why you have Nb laser with Ytteria. So, we have Nb YVO4V. So, when we have this laser, they are neodymium. It is neodymium laser. So, neodymium is the common dopant in commercial lasers with ytterium, which is YVO4 and lithium fluoride YLF and ytterium aluminum garnet YAG. So, all these things are pretty common. So, Amandeep, while correction, I think it is D, please check. So, it is Nd-YVO4 Nd-YAG Nd-YLF. So, these are some of the lasers which you see commercially available. So, all these things have their own lambda So depending upon the lambda, you can try to use it. So here in a solid state laser, you will have, this is the gain medium. So you have a pumping cavity, it can be light or it can be electric. So then, as I told earlier, it was 100% reflection, it is partial reflection, it goes back and forth and exits a beam out. So this type of laser, here you have a solid. So this is what we had is Nd-YAG VO4, you can have it. Okay. Solid state laser operates at different wavelengths, that is why you have different materials depending upon the dopant and host material. So these two dictates the lambda. Doped YAG and YLF produce laser beam with 1064 nanometer and 1054 nanometer. There are certain applications depending upon the wavelength processing will happen. Ti3 plus dopant ions in Al2O3 produces 780 nanometer, while ruby laser produces 694 nanometer. So all these things come in the, so we talk about 400 to 700 nanometer. This is the visible range. So now we are talking about 1000 is here, 1064 is here. When we talk about blue laser, they form under 254, 248, all these things are UV laser or blue laser. You can have something around this. So this is 400 nanometer, 700 nanometer, this is the working range or the visible range. You are now talking about lasers in this place. 1064 is YAG, then 1054. If you take it, this is somewhere around about here, which is Ti doped AlO3. When you take ruby, it is somewhere around about 694. So each of these wavelengths are very important when it starts interacting with the workpiece material. So here it is a powder. So the other interesting thing is, suppose you have a metal powder, you have a ceramic powder which is there. This is metal, this is ceramic, this is metal and this is ceramic. Assuming for discussion sake, these are all metals, metal powder, and these are all ceramic powders. If you want to melt only metal powders, you can do it depending upon the wavelength. So Nd-YAG solid state laser, they will have a flash lamp which excites Nd ions. Electrons reach the highest energy level of E4, 4 level, which has a 250 microsecond lifetime. So you see from E1 to E4, E4 to E1. So 250 microsecond will be the lifetime. Electron decay, non-radiation to metastable energy level to E3 with a longer lifetime than E4. Therefore, population inversion results. The electron from E3 will decay after some time in the lower level E2 through spontaneous emission, emitting a photon of wavelength 1064 nanometer. So Nd-YAG comes with 1064 nanometer. It is 4 level laser used for prototyping. E2 has a shorter lifetime and the electron quickly decays non-radiative to E1. So E4 to E3 non-radiative, E2 to E1 non-radiative. So what thing happens is from E3 to E2 only. So Nd-YAG laser is very common. It is a solid state laser. It uses 1064 or it throws out 1064 nanometer. So this is what is the diagram. E1, E2, E3, E4, pumping band, it comes to E4, pumping action takes place. From here it falls to non-radiative decay happens to E3. From E3 to E2 it falls, emits radiation, laser transition, and then from here it falls down. Energy level diagram for neodymium doped YAG laser is this. So when you buy laser, you should also look at the type of laser and the wavelength of laser. Let us take the other laser which is called as disc laser. Disc laser or active mirror are solid state lasers with a heat sink and a laser beam released on the other side of an active gain media is disc laser. So here also it is a solid state laser with a heat sink and a laser beam released on the other side of an active gain media. The beam is not necessarily circular. So, this is another interesting learning you are having now. Beam need not be circular, it can be also oblong. Beam can also be split. Beam can also be concentric. Depending upon your requirements, you can change the shape of the beam. Optically pumped semiconductors are active media. The disc laser are very efficient and small, but the power is limited because we must transfer the heat out of the setup. Disc lasers are popular in AM, especially LDED, laser directed energy deposition, due to their high wall plug efficiency. It is because of this disc lasers are also effectively used. Next laser is gaseous laser. We are talking about CO2 laser. In gaseous laser, the gain media is gas or a gas mixture, and depending on the gas used, they can be divided into atomic or molecular gaseous laser. So, CO2 is one example, and then here it can have atomic laser or molecular laser. Molecule is big, atomic is small. Okay. Helium neon and argon ion gases are atomic gases, whereas CO2 and excimer laser are gas laser, which is molecular laser. Excimer laser, excimer is nothing but excited dimer. So, dimer, krypton fluoride gas comes, it tries to activate, tries to take you to population inversion, and then you try to get it. So, you have helium neon and argon ion lasers, and you have CO2 and excimer lasers for molecular lasers. In gaseous laser, the power will be generally low. Low pressure gas is contained in the cylinder with 2 electrodes. This is what I said, you have a container, you have electrode, you pass current, and then you try to activate whatever you want. So, an electric discharge inside the gas tube creates a current that ionizes gas atoms to form free electrons that travel from the cathode to anode. So, discharge means it reaches a stage and it starts discharging. That means to say, in between the 2 electrodes you will have air. This dielectric has to be broken. When it breaks, it tries to create a discharge. An electric discharge inside the gas tube creates a current that ionizes the gas. The gas here is ionized. So, what do you mean by ionization? Ionization of gas is nothing but plasma. Ionized gas atoms to form free electrons that travels from the cathode to the anode. After colliding with free electrons, some atoms decay to lower energy level. When laser theory conditions are met, the population inversion causes lasing action. This is CO2 laser, gaseous laser you can do. CO2 lasers are operated at 11 micrometer and 9 micrometer wavelength. Micro. So, mu is 10 to the power 6. When we say nano, it is 10 to the power minus 9 meter. So, try to have this conversion, okay, at 11 micrometer and 9 micrometer wavelength, and with 100 kilojoule of continuous laser, 100 kilojoule or kilowatt, with 100 kilowatt or 10 kilojoule continuous wave or pulsed power supply. Most of the additive manufacturing machines uses 10.6 micrometer as a wavelength. The molecular gas laser structures are longitudinally excited, waveguides and transverse excitement happens. The longitudinal excited laser, the gaseous laser medium is enclosed in a long narrow cylinder. So, it is like this, long narrow glass cylinder it is that, and then you fill it up with gas, you excite it either by light, flash lamp or by excitement. This is the glass tube. So, this is the glass tube. So, you can see gas in and gas out happening. So, you have anode at one side, cathode at one side. This is 100% mirror and this is partial mirror. So, it goes back and forth, back and forth, back and forth, and then it exits out. So, gas in, it can be a CO2 gas, gas out can be the split gas, whatever it is gets dissociated and then it comes out. So, this is called as CO2 laser. This is also effectively used in additive manufacturing, and in DED process majority of the time they prefer to use CO2 laser, but the only limitation of CO2 laser is it occupies a huge space and it is also not very high energy efficient. So, the other way around is you can also have transversely excited CO2 laser. So, you can see here this is a mirror, the gas comes in, it goes through the uniform chamber and it gets out, the gas gets out, the electrodes are placed and rest all things are same. So, this is transverse type, this is longitudinal type. So, if you see longitudinal, anode, cathode, transverse anode, this is anode and this is cathode. Okay. The electric discharge current is applied through the glass tube electrode. In sealed laser system, the tube must be changed periodically to prevent electrode corrosion from CO2 breakdowns. Recirculating gas through the tube preserves gas in another system. Waveguide laser with a waveguide gain media can produce continuous phase CO2 laser. In this type of laser, that means to say CO2 laser, the bore region is between radio frequency electrode. The bore region is between radio frequency electrodes. Connecting the electrodes to an 80 to 100 megahertz RF power supply creates a high frequency alternating field. Okay. 80 to 100 megahertz frequency, RF frequency, you do it. So, it tries to generate a high frequency alternating field. Small bore dimensions ensure efficient laser gas cooling and high pressure operations, leading to a high gain and 100 kilowatt power output. Transverse excited lasers uses gas at 1 atmosphere or higher, the parallel electrodes a few centimeters apart. So, this is for transverse. Okay. Transverse is, it is on the side. Transverse is, this is one electrode, this is one electrode and you have glass tube inside. This is electrode and this is also electrode. Glass tube. Okay. Transversely excited laser use gas at 1 atmosphere. Pre-ionized gas between the electrode ensures a uniform discharge when high voltages are applied. This is quite common in CO2 laser, or I would say in excimer laser So, here what happens, you have a cylinder, pre-mixed cylinder, krypton fluoride. So, the gas goes into the tube, this is a glass tube, and in the glass tube you have electrodes through which there is a discharge happening. This is a glass tube. This is a cylinder and it is cylinder. It is pressurized. So, the tube goes like this. Okay. So, pre-ionized, the gas between the electrodes ensures the uniform discharge when high voltages are applied. This configuration has been used in some excimer laser to produce high energy pulsed laser. These lasers have the same excitation mechanism. In this system, the laser gas is 0.8 to 1 mixture for CO2 and N2. N2 boosts large efficiency to 30%. The excited energy level of nitrogen is close to the vibrational level of CO2. So, we use the premix of CO2 and N2. N2 excited level is metastable to reactivate decay, and collisions transfer energy to the CO2 vibrational level 001, causing population inversion. The possible laser transition in CO2 laser are the two 001, 100 and 001, or this can go to 020. The transmission which is emitted is 10.6 and 9.4 microns laser beam. We also have liquid dye laser. In this liquid dye laser, we always try to use a organic dye laser. Organic dye laser or dye laser uses system in which the lasing media is liquid at room temperature. So, what we do is we try to have a grating, we try to have a beam expander, then we have pump in the beam which happens, we have a lens. So, here is the dye cell. This dye cell will be given a light which tries to excite the dye which is here, which is an organic dye, which tries excited, and when this gets excited, it tries to eject out a laser output from the output coupler. So, dye lasers, they are generally used for pumping. Dye laser can pump another laser, and this will be a pumping source for getting excited. People use that, but generally dye lasers are not very high power, and it is used for marking, gradation or diffraction patterns, then gratings, all these things are done. Typically, a gain media is an organic dye solution with strong absorption and emission properties. According to the type of the dye used, a wide range of wavelength can be achieved. That is the beauty of this. You change the composition, you try to get different wave length, but the only thing is the powers will be extremely low. Using various dye sequencing, a tunable laser output extended from 320 to 1. So, this is called as tunable laser. Tunable laser means you can try to change the wavelength depending upon the dye you use, and this is very important, because when you are trying to do additive manufacturing, you might have to use varying wavelengths to meet out to the requirements. At that point, this type of lasers come handy, but the power what is there is very low. People are working on it to try to accelerate or make the power high such that it can be used by a tunable laser output. Such lasers need a high voltage, low current power source as well sizable storage capacitor. The frequent dye used in these lasers are rhodamine B. Dye laser can pump by other lasers and come in pulse, continuous or mode locking forms. Medical and material texturing are two big fields used for this dye laser. The last one is going to be semiconductor laser, which is very common today is semiconductor. We have a P type, we have a N type, and in between the P type and N type I have an active region. So, there is a voltage bias which is passed to the metal contact on the top, and at the bottom you will have metal contact which is taken from N, and then you try to pass a voltage which tries to move the electrons from top to bottom, and this tries to hit at the activation region, and what you get is a beam, laser beam, which gets out of this activation media. So, semiconductor laser P type, N type, P junction, N junction, active media in between, voltage is applied in the metal contact. So, they try to push in, and through this you will try to have a lasing media which comes from the active region. This is becoming very popular, and this is very high or very good in energy efficient. Lot of new laser additive manufacturing machines are getting attached with diode lasers. So, it is also called as semiconductor diode lasers. Diode lasers are small, efficient, requires lesser power than the other lasers. In this type of laser, gallium arsenide or semiconductor chip are used. This is very important because they are small, energy efficient, requires lesser power than other lasers. So, it is very efficient, because when we talk about sustainability, we always look for low power lasers, but you get this power for low power means I am talking about in low power. What gets out of the machine will be high power. The laser can be electrically or optically pumped, which we have discussed enough, and the lasing media is a PN junction made out of 3, 5, 2, 6 semiconductor groups. When current flows through a PN junction, electrons are excited to a higher conduction band state, then decay to a lower state. So, from a higher conduction band to a lower state it happens. The valence band hole moves up at the same time. The recombined electrons and the holes emits photon near the material band gap. This is an important point. The previous one is also important. This is also important. When a current flows through a PN junction, electrons are excited to a higher conduction band state, then decay to a lower state. Next, the valence band holes make up at the same time. Holes also make up. The recombined electrons and holes emit photons near the material band gap. The process can be spontaneous or stimulated, leading to an optical amplification. So, optical amplification is very important word. The beam is not round, the laser is achieved up to 40 half angle beam divergence. 40 angle means we are talking about beam divergence. This is beam divergence. The non-symmetric beam distribution is possible. So, here you should also understand the beam is not round. So, I have to do something to make it round. So, basically laser, then you will try to have optics, and then you will try to have an output. So, this optics can be a beam shaper. Beam shaper. Non-symmetric beam distribution is also possible. So, that means to say you can convert Gaussian distribution into cowboy hat pattern, or you can try to have a skewed distribution also. Non-symmetric beam distribution is possible. Low energy per area is the feature of this laser. Depending on the material, energy band gap, emission wavelength can be varied. So, whatever we are trying to talk about material band gap, this tries to play an important role in wavelength. Fiber optic laser, it is the latest. Semiconductor, then came fiber optic laser. This type of laser uses only a fiber optics. Fiber optics means a glass fiber which is having a diameter of maybe 0.3 millimeter, it can go up to 2 millimeter, something like that, right. So, fiber optic cable. Fiber optic cable you can also, you would have seen in the as a toy also. So, you would have seen there will be a light source. In this light source they will attach it with fiber optic cable. So, you will see at the end of the cable as though something like a droplet of light there. A droplet of light. So, this is all optical fibers. Optical fiber doped with rare earth ions such as iridium, niobium, germanium, ytterbium and other continuous semiconductor diode lasers to pump light to the core section. So, light to the core section. So, here is light. So, there is a core section. This laser creates short pulse. Fiber lasers can use a fiber as a resonating cable. So, what you saw a long longitudinal cable for CO2 and transfers, here you use a fiber itself as a resonant cavity. A 2 kilowatt continuous fiber laser with 50 micron spot with 100 megawatt per centimeter square power density can be achieved. So, look at it. This is also now gaining importance in additive manufacturing. Small dimensions and scalable power make this laser a suitable replacement for solid state and molecular laser. So, if you look at it, today we use CO2 seldom, fiber optic laser, this is first of its kind. Next, we try to use semiconductor laser. The last one we try to use is solid state laser. So, these are the three types which are commonly used in today's additive manufacturing process. For pumping, you use a dye laser. CO2 laser is also slowly dying because of its efficiency and a huge space required for making the setup. So, these three are going up and down, and depending upon the dopant, depending upon the gain media you have, you try to get multiple wavelengths. So, this is a fiber optics. So, you have a pump source, you have a lens, it passes through the optical fiber. The optical fiber itself is a resonating cavity. So, you have a medium which tries to push. So, you try to have a lasing action inside, and what comes out of this is nothing but a laser beam. This is a fiber optic cable. This is fiber optic lasers are gaining more importance on top of solid state laser. Semiconductor laser is also coming up, but fiber optic is the outstanding now. Due to different indices of refraction for the cladding and core segment, a laser beam pumps into the cladding, which will bounce and rebounds inside the core. So, what we are trying to say is, inside this cable it will bounce, rebounds. So, this is the cable or the optical fiber, and this is bounce and rebounds. Okay. Cladding will bounce and rebound inside the core. The core absorbs pumping light each time the beam passes through it. Two fiber grating. What is fiber grating? You have this, two different fiber gratings will be there. Gratings are nothing but small lines which are drawn, where it will have transparent and opaque. When the light passes through it, it creates a diffraction pattern. Two fiber Bragg gratings act as a wavelength mirror in the fiber laser. So, this is the wavelength, the partial whatever we saw, mirrors. So, wavelength mirrors. The atom level of earth elements have extremely efficient energy levels, allowing the use of inexpensive diode laser pump source to provide high output energy. It can also use multiple pump fibers connected to a coupler. So, this is a coupler. So, this is a multiple fibers attached to a coupler. You can have gratings, and this will try to create a beam. So, this is rotated and kept, so that the length is now converted into rotation. This is length. So, this is rotated. So, you occupies a small space. So, you try to get, and then finally you get a beam output. So, here lambda power is very important, and of course, spot size also. Okay. So, this is a fiber laser that induces FBGs and beam couplers. So, the Y beam and ER fiber lasers are very common. So, most industries use ytterbium and erbium fiber lasers. Single mode ytterbium lasers are popular in AM. So, as I told you, fiber laser in additive manufacturing is going to be there. So, here I have said E0 or E1, E3, E2. So, non-radiative, this is radiative. You see the wavelength what comes out. So, single mode laser distribute energy perfectly Gaussian. In fiber laser, the gain medium is the fiber optic connected to a pump source and an optical resonator. The continuous wave diode laser pumps the fiber and amplifies the pulse through the system. Diode laser pumps the fiber and amplifies the pulse to the laser. This type of fiber laser excitation mechanism is explained by its energy level diagram. So, this is what it is. So, erbium doped fiber laser is 3 level, which we have seen. Optical pumping excited electron from the ground state to the excited state at 908 nanometer, non-radiating electron decay to the upper laser level of 413-2, causing population inversion between 2 and the ground state 5. The photon with an 1550 nanometer wavelength are emitted and amplified in this condition for usage. So, if you see the laser type, And if you see the two prominent process, one is called as laser powder bed fusion and DED. You can see here it is CO2 laser which falls here, DED, and then you have continuous CO2 laser, then you have continuous wave fiber laser which falls in powder bed, then you have diffused cooled slab CO2 laser again in DED. DED and all is very high power. Then you have fiber coupled diode laser for DED, then you have Nd-YAG laser for powder bed fusion, then pulsed Nd-YAG laser for powder bed fusion, and I have told you what is the source, T active media. Then you have Q switched Nd-YAG laser which is there for cobalt which is used as the dopant. Yttrium fiber laser, it is also used for powder bed fusion. This graph tries to talk about laser employed in laser based additive manufacturing in powder bed fusion and directed energy deposition. So, now let us see the last part of the lecture, which is on laser beam properties. Laser beam is a coherent, monochromatic or monocolor collimated extremely parallel light which comes out. The lasing media is placed in the cavity or resonator with two parallel mirrors at each end to amplify light. The presence of these mirrors creates transverse mode superimposed on the beam. So, mirrors create transverse mode superimposed on the beam known as transverse electromagnetic mode. Okay. This is very important. So, creates transverse modes superimposed on the beam. So, this is called as TEM. Gaussian Legrer modes are given as TEM-PL in the laser. P and L indicate the number of zero intensity nodes transfers to the beam axis in the radial and tangential direction respectively. When you buy a laser, there will be in the specification TEM 00 mode. So, this TEM is nothing but transverse electromagnetic mode which is caused by transverse modes superimposed on the beam. Okay. So, this 00 is nothing but P and L, which indicates the number of zero intensity nodes transfers to the beam axis in the radial direction and in the transverse direction. Radial direction and transverse direction. Now, let us see some of the modes. So, for TEM 00, P and L are 0, representing the lowest order with a Gaussian beam distribution. This is commonly used mode for additive manufacturing with respect to metals. Different TEM modes have different energies and patterns. The Legrer equation describes the intensity distribution of a TEM 00 or PL mode at a point R and psi in polar coordinates from the mode center. So, it is represented as this. You have I naught, which is the beam intensity which is decaying with respect to time. I naught is the intensity scale factor which is watt per meter square. Ri is the radial. So, this Ri is the radial. So, this is the laser beam coming and this is Ri. Ri or RL is the radius of the laser beam profile. M2 is the beam quality factor. LPL is the associated Lagrange polynomial in the order of P and index L. This is very important. When you buy a laser, you always ask for the mode of the laser and then you will try to ask what is the m square value of the laser. You will try to also ask what is the profile it follows. So, the profile following will be found out by solving this equation, or you can ask them, they will say it is a Gaussian distribution. But TEM 1100 mode itself predominantly is dominated by a Gaussian distribution. So, I naught is represented by this way, where L going from 0, our L taking a value 1, 2, 3, 4. PL is the net laser power. Longueur polynomial can be expressed by one of the two equations like this or like this. In the examination, we will try to have a small math problem to be solved such that you try to figure out what is your I naught. So, the various modes which are generally available for laser, the most common one is TEM00 mode. The cross section will be like this and the Gaussian distribution will be like this. This is called as I naught and this is called as the radius r. The m square value is 2. Generally, the m square value should be close to 1. 2 means the beam is not going to give you a good result when you finally develop the part. TEM10 mode, you have a center one and then I said in the radius, this is P and L. If you go back and see what is your P and L, this is your P and L. P and L indicates the zero intensity mode transmission of the beam axis in the radial and tangential direction. So, now let us see the TEM10. So, this is 10 which is you have double circle. You can also have TEM11 which is cut into 4 peaks. If you want to have very precisely doing, then you can have this. So, depending upon the choice of the mode, you can also dictate the quality of your output. You can see TEM. So, what are the combinations? It is very easy. 0 0. So, 1 0, 0 1, 1 1, right. So, and then you can have 0 2, 1 2, 2 2. So, you can keep on be adding. So, this is we have seen 0 0 mode. 0 0 mode is very straightforward, which is this, and 1 0 mode is this. 1 1 is you are cutting it into 4, 0 1 is you will have a peak like this, and if you have TEM001 star, so then you will have a cowboy hat pattern. This is something like a cowboy hat pattern, and TEM102 you will have a pattern like this. And all these things are important because all these things try to dictate the melting or the sintering process when we use the beam. The radius of a laser beam, so you have a spot, the radius of a laser beam is always represented by R1 or Ri depending upon the propagation axis, and which can be expressed in this form, because the spot diameter is very important. The TEM00 and all is within the spot whatever you are trying to get the profile. So, the waist of the radius is r square in location along the propagation axis of Z0. The far field divergence is theta. Okay. So, this is what we express through R1. R1 can be calculated from R0 plus theta. Theta is the beam divergence. Z minus Z0 is the propagation axis, and Z minus Z0 is this along the Z direction. Okay. The beam quality which I was kept on repeating, m square, can be written as 1 by q, and this will be written like this. So, the medium laser wavelength lambda and the reflection index n can be defined as a parameter called k. So, k is equal to 1 by m square, which is this. K is equal to m square equal to 1, the beam is Gaussian, whereas non-Gaussian or not Gaussian is values will be taking values greater than 1. The larger the m square value, the beam shape will become similar to a flat hat. Therefore, the depth of focus parameter in a parabolic beam profile with respect to the segment of the beam, that can be assumed to be a cylindrical shape. Very, very important points. Please make a note. The depth of focus parameter in a parabolic beam profile which refers to the segment of a beam that can be assumed to be a cylindrical shape. So, this is what is the diagram which we talk. The depth of focus for a 28 degree theta. So, this is theta, 28 degree theta. So, this is how you project it. This is the Gaussian distribution we follow. This is I naught or In, and this is Z, and this is Z0, and this is Z1, and this is the RZ radius. This is the beam divergence. So, the depth of focus, you can try to say between here to here. This is a region where you can focus the sample. The depth of focus for a 28-degree angle of divergence is reported to be approximately 1.0 times 1 times R01. So, to come to a conclusion, till now what we saw in the 2 lectures are going to be various subsystems. Then we saw about types of laser and its component, then difference between continuous and pulsed laser. Today we use exhaustively pulsed lasers, properties and characteristics of laser beam. So, we also saw different types, and here we saw the properties like waste, what is it, and important properties which are needed to be known for AM. So, as and when I walk through the slides, I kept on saying this parameter is important for AM. So, that is what we are trying to talk about here. So, I am sure you will all now have a little bit of knowledge about laser, laser matter interaction, how is the choice of your laser going to affect the influence of either sintering or melting while the product is developed. When doing DED, the energies are high as compared to that of your powder bed fusion method. So, now I have 2 assignments. All these assignments you do not have to submit, it is only for you to learn more about the subject. Make a list of different types of laser used in metal additive manufacturing. So, what I am asking you is, you start looking at various machines, at least in powder bed fusion some 10 machines. 10 machines means 10 different company machines. Then DED at least look at 5. So, now what will happen is, each machine manufacturer will have at least 3-4 variations. So, try to write down all the machine model. So, model number whatever it is XXXYY. Then you try to write down the specification which is used for the machine, and in particular laser, start noting it down, and then you also try to see what are the possible raw materials which can be used in this process. When you do so, our focus is more towards laser. So, what are the different types of lasers used in metal additive manufacturing? Google and find post processing done in this metal additive manufacturing with the help of laser. So, when we start producing all these things layer by layer, you will have something called as a staircase effect, because you are building it layer by layer, right. When you have this staircase effect, you have to smoothen the surface. So, when you have to smoothen the surface, in the post processing nowadays, we also have one more laser which tries to move on top of the metal additive manufactured part, remove the staircase effect and flow the material such that it gets a very smooth surface. So, it is worthwhile for you to understand how do we do post finishing operation using laser for additive manufactured parts. If you can also make a small essay about it, understand the process, look into the laser, find out what is the difference between this laser and that laser with respect to all the parameters. This will try to give you a overall idea of the process and laser involved in the process. Thank you very much.